One of the things that makes space travel really quite difficult is that it's a long way anywhere. It might only be 8 light minutes from the Earth to the Sun. It's something like 4 hours at the speed of light to the end of our solar system, and we haven't gone anywhere. It's the distances beyond our solar system are measured in light years. That is the distance that light travels in a year. So distances are very, very large. In our own little galaxy, we're measuring distances in terms of hundreds of light years. And if we go to distant galaxies, we're talking about hundreds, maybe hundreds of millions of light years. That's hundreds of millions of years if we could travel at the speed of light. So one of the first things we're going to look at is the implications of mass dilation. Because as we get closer and closer to the speed of light, our relativistic mass dilates, it increases exponentially, getting close to infinity as our velocity approaches the speed of light. That provides, if you like, a cosmic speed limit, because the greater your mass is, the greater the force that's required to accelerate at that last little bit to get it up to the speed of light. And so when we get just short of the speed of light, it requires an infinite force to do that last little bit of acceleration. So while we can quite realistically accelerate protons and electrons very, very fast in particle accelerators, we can only get them up to close to, but not past the speed of light. So one of the implications is we can't go faster than the speed of light. Well, what hope have we got to do a journey of, say, a small journey, maybe 100 light years worth of distance? What possible hope have we got to travel that journey? Well, the implication of length contraction and time dilation actually makes those journeys possible. Because from the perspective of the astronauts, the people on the spacecraft, if they're traveling close to the speed of light, what looked like 100 light years to someone on Earth in their frame of reference, in the frame of reference of the spacecraft, that's going to be contracted enormously. So what would have taken 100 years, or a bit over 100 years at close to the speed of light, might only take you 5 or 10 years from the astronaut's point of view if you could get close to the speed of light. So it actually makes a journey quite realistic. You could actually possibly survive some period of time, maybe years in a spacecraft. You're not going to be able to survive 100 years because it'd be your children or your grandchildren arriving at the other end. So it does actually make some kind of journeys within our galaxy quite possible. And of course, with the time dilation, what that means is from the Earth-bound observers, it's still going to take, to go 100 light years, it's still going to take, let's say, 101 years for the journey to happen. But from the astronaut's point of view, that 101 years is only going to be a much shorter period of time because the apparent distance they've got to travel is much, much shorter. So the implications of mass dilation, that provides a cosmic speed limit. We can't go faster than the speed of light. But the implications of length contraction and time dilation means that it actually might be feasible to send astronauts what would otherwise seem to be ridiculous kind of lengths of journeys, maybe hundreds of light years, because if we can get them fast enough, we'd be able to get them there in their frame of reference in what seems to be a pretty short period of time. So a bit of swings and roundabouts with the implications of relativity. It means we can't go faster than the speed of light, but as we get close to the speed of light, journeys that would have seemed insurmountably long now in that frame of reference may well be quite achievable. The problem is trying to get a spacecraft to anything like the speed of light. We haven't got anything close to that. So it's about 1 million times faster than the speed of sound. The speed of light is incredibly fast. And sure, we've got electrons and protons and subatomic particles very, very close to the speed of light. It's quite a different matter to accelerate something with a mass of 10 to the minus 31 or 27 kilograms. It's a very different thing to accelerate a physical object with people in it. The amount of fuel required to accelerate you up to speeds close to the speed of light would be just mind-blowingly, astronomically huge. So the practicalities of getting us travelling close to the speed of light might actually mean that those kind of long journeys that relativity makes possible, maybe they aren't possible after all.